everyone. Today we are going to present our PBL topic cloud-based crop yield prediction and disease detection presented by H. Neha, Nisha Nitya and myself Samya. Next we'll move to the contents. Overview of our presentation. We'll begin with the introduction, then the problem statement and objectives. After that, we'll discuss the literature review and the proposed system design. We'll also explain the architecture, technologies used, dataset methodologies, and yield prediction, cloud integration results, and finally the advantages and conclusions. So the next slide is problem statement. In agriculture, one major problem is that farmers are unable to accurately estimate the crop yield before harvest. Additionally, sudden plant disease like blight, rust, and mosaic can spread very quickly, which leads to several crop losses. Right now, disease detection is mostly done manually. This process is slow, depends on experts, and cannot be used for large scale farming. Also, agricultural data sets are very large, so high storage and computing power are needed, which traditional system cannot handle. Therefore, there is a need for an automated cloud-based system that can remotely predict crop yield and detect plant disease accurately. Our project aims to achieve the following objectives. First, to predict crop yield using machine learning by analyzing multidimensional data such as soil parameters, weather details, and crop information by leaf datasets. Second, to detect the plant disease using deep learning, specifically CNN-based image classification of leaf images. Third, to make use of cloud services so that we can store the large amount of data, train models efficiently, and deploy the system easily. And finally, to provide real-time results through a dashboards or mobile app so that farmers can instantly access the predictions and disease information. The system helps improve decision making in irrigation, fertilizer planning, harvest timing, and disease control. Overall, it reduces farmer losses and increases crop productivity. Related to our topic, past studies shows that machine learning models like random forest, gradient boosting, and achieved high accuracy in crop yield prediction. For disease detection, deep learning models like VGG16 and ResNet works extremely well with plant leaf images. We also found that cloud platforms like AWS and Google Clouds are commonly used because they support large storage and high performance computing for training ML and CNN models. The gap we identified is the most existing system only focus on one area, either crop yield prediction or disease detection. Very few systems combine both features in one single platform, so our project bridges this gap bit by integrating both yield prediction and disease detection together using a cloud-based approach. System design. This slide explains the design of our proposed system. The data collection module gathers the required information like leaf, soil moisture, temperature, humidity, crop type of the leaf, and also captures leaf images for disease detection. The cloud storage module stores all the data securely on Google Cloud so that the large data set can be handled easily. The processing model consists of two models, a machine learning model that predicts the crop yield based on input parameters, a CNN model that detects and classifies plant disease using the uploaded leaf images, the system that shows all results on a dashboard, which displays the yield prediction, disease type, and gives prevent suggestion to farmers. Finally, a notification system sends alert messages to the farmer if any disease is detected or if immediate action is required. Overall, the design combines both prediction and disease detection in a simple and efficient cloud-based workflow.
From the moment farmer uploads the information to the moment user sees useful results on their device. First step, the farmer uploads the data. This is the starting point. The farmer uses the mobile phone to upload the pictures of the crops and other fields data. This data is like raw ingredient. That next second step will be the data stored on the cloud. After the farmer uploads the data, it goes to the cloud, which is like a giant online storage box. Here it is kept safe, secure, and ready for processing. Then ML models run. Now the machine learning models start working. They take the stored data and analyze to detect crop diseases, plant health, and expected yield. Next, fourth will be the results saved to the cloud. The cloud, once the ML model finish their analysis, the output results are again saved back to the cloud. The result will contains the prediction and insights ready for user to see. Then next step, the dashboard will fetches the result. The dashboard now connects to the cloud and fetches these results. Think of it like a the user can see the three outputs like the disease prediction, what is the disease and what is the recommendation they can get and how much will be the yield. The three alerts will be given. So next slide I will be telling you what and all the technologies used. Though
Change
the
the slide in
slides.
PPT.
This slide how entire the agriculture prediction system is arranged inside the cloud. The cloud will works like a central brain where the data is stored and it is processed and it is delivered back to the user. When the farmer uploads the images and crop information from the app, the data from the web, the data will first goes to the cloud storage, which acts like a safe folder, and it is sent to the machine learning engine, where the ML model will perform the disease detection and yield prediction. Once the model finishes processing, the output is again stored in the cloud storage or the result database. On the user side, a dashboard or a web app is communicates with the backend APIs to fetches these predictions. The dashboard then displays the insights, alerts, and recommendations to the user in a readable form. This architecture shows how the system moves data through different cloud components, storage, processing, ML, and dashboard, ensuring that fast performance, scalability, and secure data flow. The next step will be data description. So the slide describes the complete machine learning workflow in your crop yield prediction system, starting from collecting the data, ending with cloud deployments. First, the data collection is done using the reliable sources such as the leaf datasets that is cloud. This gives the model inputs like the different types of leaves like based on the shape or the diseases. Then the values are normalized to a similar scale and the most important features are selected to improve the model performance. After the data is cleaned and prepared, the next step is model training, where algorithms such as linear regression, random forest are used. The data is split into 80% for training and 20% for testing. To ensure the models learns well, it is evolved properly. Once again, it's complete. The model is checked using evaluation metrics like RMSE and MAE and R square. Score to measure its accuracy and error levels. After confirming the model's performance, it is exported and deployed on a cloud server where the API is created. This API allows the real-time predictions, meaning the users can send input from a dashboard and instead receive yield predictions and from the deployed model. Now we'll be showing our website. So first we'll click on the start analysis. Then it will ask you to upload the photos. Then you can will be uploading the data. So you can give analyzing this. So it is detected since there is a healthy and it is the prediction is 0.5 and it is giving you recommendations, what and all the recommendations you should give. Moving to another news. So for this saving road thought, so the yield reduction is 50%. Then the recommendation will be improve, avoid drainage and avoid over watering. So what kind of the recommendation we can improve its yield. And the plant health is this much and the severity is this much. So how it works, like we will upload the image, then it will do analysis, then it will give it. This is our website.
Yes, I'm going to take you to the methodology part. This slide shows the complete workflow of our project. First, data is collection, like the data is collected from cloud APIs and datasets. After that, we pre-process the data to make it suitable for machine learning. When then we then apply ML models like linear regression and random forest for yield prediction. For disease detection, we use a deep learning based models like CNN models where the leaf image is fed into the network and classified based on the diseases. So if it is diseased, it goes to disease part. If it is not, it goes to healthy part. Like after that, after training, both the ML and CNN models are integrated into cloud platforms. When farmers enrolls the soil and what weather details or upload a leaf image, the cloud host model pre-process the input and returns a predicted instantly. All results are displayed on the dashboard with the graph, charts, and suggestions for the farmers for the development of their crop. So this is about the methodology. Cloud integration. So here is the question called why cloud? Because cloud integration plays a major role in making soil scalable and efficient in agriculture data. Because agriculture data is very large and machine learning models require high compatible power. It is all these large data sets we use. For that we will be using cloud services. So cloud features, what are all we used? Like for storing, cloud storage is used to store database and thousands of leaves images are stored. Cloud computing engine is used to train ML and CNN models faster when compared to others. And also cloud functions automate prediction makes, and finally APIs helps delivery predictions mobile or web applications in real time. Fine. After that, using cloud gives us several benefits like faster processing. Um, Compared to other APIs, cloud will be processing the data very faster. So faster processing is seen in the cloud, high accuracy, remote access, low operation cost, and also some what we call easy integration with future former devices like sensors and drones. Also, we can see in the clouds. Right? Next, I'll be explaining you results in the output part. Yes. This slide presents the output of a model like a crop yield prediction, random forest, the best and achieved around 85 to 90% accuracy. The system predicts the extended crop yield to tons like per hectare based on soil and weather conditions. For plant diseases and detections, our CNN model performed explicitly will well with like 92 to 95% accuracy. The output includes the disease's name, severity level, and recommended treatment for the disease if it is diseased. Like this helps farmer to take action before the disease spread to whole his crop. Next, the dashboard displays multiple visualizations such as temperature versus yield, graph, diseased, and probability charts, and also real time alerts. we can see in our output. So overall, the result shows the system in reliable and highly beneficial for the farmers. So I would like to explain also the advantages. Yeah, before I go into the conclusion, I would like to explain about advantages. Advantages, some of the major advantages of our systems are accurate prediction of the crop yield before harvesting, and early detection of the plant disease using deep learning. Also, we can say like cloud-based design makes the system assemble for anywhere and saves time by reducing manual monitoring, helps farmers optimizing irrigation, fertilizer used for harvesting and all. So reduce crop loss and increase productivity more than the manual checkup. So with all these benefits, our system supports modern data drives smart agriculture. Like so I would like to conclude now. To conclude our project successfully, integrate machine learning, deep learning, and cloud computing into unified platform. This system not only predicts crop yield but also detects the plant disease with high accuracy, and also it provides real-time insights and increased productivity and help farmers for making information decision. So overall the project shows the how technology can transform traditional farmers into more efficient smart processing. This is what I can conclude for the project. And next, when I go to references, the references we used are including research paper on deep learning in agriculture data sets from Kaggle and Plant Village uh, websites, and cloud document from Google Cloud and AWS. These sources helped us to design and improve our system very much. So this is about the project. I thanking you everyone for the attention. Thank you.